Hi, my name is Stephen Heitch, and this is my Lab 5 on air pistons. So as our outline, we'll go through an introduction, the main physics principles, the experiment and data that was collected, some errors, and the results that we found. So as our introduction to this lab, the purpose is to understand the similarities between air and a spring when used in a syringe with the end blocked, and we will use the energy principle to calculate the stored energy in that syringe. Our main physics concepts are the energy principle and the spring force and potential energies formulas, and then we'll use the tracker data of a real syringe pushing a cart down a track to measure how it actually worked. And then our results is that a spring seems to work, a syringe seems to work fairly well as a spring, but it doesn't store a whole lot of energy, but its forces are fairly high. So the main physics principles we see, we're assuming that there's no forces other than the spring force provided by the syringe. So we have our spring force as our negative KSL hat. Through the energy principle, we know that our change in kinetic energy plus our change in spring potential energy should be 0. So when we solve it around, we find that our final kinetic energy will equal our initial spring energy, and we can solve that for our K value for this syringe with the air inside of it. And we're assuming that there are no other forces again, and that the mass of the syringe itself is negligible. So for the experimental data, we took a cart and we set it on a track. And we pushed it into a syringe, forcing the pressure to increase. So we pressed it back and then let it go, and it went down the track. And as it moved, we recorded it and exported that data into Tracker so that we could get an idea for how it moved. We set our initial X position at 0. The syringe was compressed by 0.04 meters. And once the moment that it stopped being pressed on by the syringe, we called VI, and we found that that was 0.75 meters per second based on the X and T values we had. And we're ignoring Y and Z because there's no motion in those directions, as the track only let it move in one direction. So this is the recording of our experiment. We simply press it against that syringe on the left side, and then we let go, and it pushed it down the track, and you can see how it moves simply in the X direction. So as our calculations, when we see that the system is defined as the cart and the syringe, we can see that our Kf equals USI. And when we solve this, we can find, we knew that the mass of the cart was 0.5 kilograms. So when we plug in all of our data, we get that it stored about 0.14 joules of energy, which is not a whole lot, but it is a fairly small syringe. When the system is still defined as the cart and the syringe, we can solve this around a little bit more and find the K value as mv squared over s squared. And we know the mass, we know the velocity, and we know the compression of our syringe. So when we plug all those things in, we can find that our K value for air in this syringe would be 175.78 newtons per meter. And this is probably not accurate for air everywhere, as it's probably not linear, and it scales with the size of the syringe itself. But for this syringe, compressed all the way pretty much across the black lining, this is what we get. And then for our final one, we define the system as only the cart, and then we know that our final kinetic energy will be equal to the work done on the system. The only work will be done by the syringe, so we can solve around our F dot R to find our average force. We find that that was 3.52 newtons, which is kind of a lot for how small of a syringe we had. And then when we solve that the pressure will equal the force over the area of the thing that it applied the force to, which in this case was the plunger, which had a radius of 0.015 meters. We found that our average pressure was 4,980 newtons per square meter. So some comparisons and errors. If we used a different syringe, the compression distance stayed the same, then the final kinetic energy would probably still change, because it'll change with the size of the plunger, the length. A lot of things will have variables in it. So our total volumes will change when we use a different syringe. So the energy we store in it will change. For air to have a K value is kind of an odd thing, as it's probably not linear and it is dependent on the size of the syringe. But it is a good comparison if we were comparing a spring and using an air cylinder in the same setting. And just wanted to know which would act more favorably for us. Some errors that we might have seen are the quality of the video and the frame rate, how square it was to the track, which could have led to errors in the kinetic energy calculations, and then lots of forms of resistance would have led to lower values than we actually or would have led to higher values than the values we measured. So our general results is that the syringe didn't hold very much energy, but it's partly because it's a small syringe and we didn't compress it very far realistically. And the syringe seemed to be able to create a large amount of pressure and force, which explains why they can be used as air pistons to move things. And a better quality video and more syringes and more test runs would help us build a better and firmer relationship. Thank you very much.